Hey everyone, today I want to tell you about something very interesting about uncountable infinity. Now, I did videos about uncountable infinity before, but what's really interesting about uncountable infinity is that it can never be put into order. You can never place it into smallest to biggest. And here is an example. Okay, you see there. You see here, uncountable in. You see, it's infinity. Uncountable infinity can never be put into an order. Hence, why it's called uncountable. Because if it could be placed in an order from smallest to largest, it wouldn't be uncountable. It would just be countable infinity, just like the natural numbers. But here's what I'm talking about. Imagine I had a You see, what's really interesting is here's what it is, guys. Here's an example of why it cannot be ordered. For example, here you have at the start here you have where it says 0.01, then you have 0.001, then you have 0.0001. Do you see what we talk about? So next will be 0.00001, and the next will be 0.000001. So that's 5 zeros after the decimal point. So what number does this one get? It can't be 0.10,000 zeros 1, because 10,000 zeros 1 will be already in that line. It cannot be that. You cannot have a trillion because they'll already be in this first column. You cannot have a Google because they'll still be in this first column. So what does this one get? Well, in fact, this is why you cannot order them. There is no smallest to biggest. Directly after 0, there is no next smallest, because you'd always find a smaller one after that one. Hence, always adding more zeros after the more. And this cannot be called 0.infinite zeros 1. That just would not make any sense. Which is why we cannot have 0.infinite zeros 1, because that does not make any sense. And another way to describe it to you, for example, guys, if I did this. 0, okay, for example, guys, let me give you an example. 0 equals 0.00000 dots and recurring. So 0, what you see here is that 0 equals 0.000, and that dash there means recurring, so it's recurring with zeros. It can't be infinite zeros and then 1 at the end of that. It just doesn't make any sense. With just endlessly infinite zeros, that's what zeros means. And for example, for a number to be smallest to biggest, it needs to find an ending, the lowest decimal place to the biggest. For example, guys, 0.00001. If you want to find something that is bigger than that, you have to go smaller. Like the 1 will be there, then the 1 will be there, then the 1 will be there, then 1 will be there. But if there's infinite zeros, you cannot put a 1. There's no ending where to put a 1 in. There's no end on where you have to put the 1, which is why this infinity is uncountable. And another very interesting thing is that these are all the real numbers, and any number you can think of is uncountable infinity. And another way to generate uncountable infinity is that if you actually power set all the natural numbers. So, for example, the subsets of 1 to 3 elements is 8 subsets for 3 elements. For example, you have nothing, then you've also got 1, then you've also got 2, then you've also got 3, then you've also got 1 and 3, then you've also got 2 and 3. 4, 5, 6. Hold on a minute. 1, 2, 3, 4, 5, 6. Hold on a minute. I'm missing something. Hold on a minute. Okay, it did take me a couple of minutes to wonder about what the problem was, but I just forgot to put 1 and 2. So it took me a bit of a while to comprehend the problem, because I was just here for a couple of minutes confused on why there's supposed to be 8 subsets, but when I was counting them, it looked like there was 7. So there you go. That's 1 and 2. That's what I've been missing. What you see right there, the 1 and 2 is what I wasn't talking about. So, and then at the end there's 1, 2, 3. So the subsets are nothing, 1, or 2. So you've got nothing. A better way to describe it is better for me to just show you. So here's what they look like, and I'm really sorry for that because. Alright. So here's what they look like. You've got nothing. You've got 1. You've got 2. You've got 3. You've got 1 and 3. You've got 2 and 3. 1 and 3. 2 and 3. And 1 and 2 is what I forgot about, which is why it left me confused. This is why I was really confused, because this is what I've been missing. 1, 2, and 1, 2, 3. These are 8 subsets for 3 elements. I think there's 16 subsets for 4 elements. I'm not entirely convinced if that's the case, but I do believe that there's 16 for 4 elements, the last. But for infinite sets, you cannot have one. For example, if there's infinite set, you can have 1, or 2, or 3. That's already infinite. Or you can have 1 and 2, or 1 and 3, or 1 and 4, or 1 and 5. That's still infinite. Or you can have 2, 2 and 3, 2 and 3 together, or 2 and 4, or 2 and 5, or 2 and 6, or 2 and 7. It just keeps going. You have, if you see the order, you can have 3 and 4, 3 and 4, 3 and 4, or 3 and 5, or 3 and 6, or 3 and 7, or 3 and 8 in the correct, exact respective place, or 3 and 9, or 3 and 10. Just keep going. You can have 4 and 5, 4 and... No, I mean, you can just keep going, which is why it's uncountable. For example, I'll have to tell you the truth. Uncountable infinity is literally bigger than regular infinity, because you can never place it in the correct corresponding order. Like I just said, there's no exact smallest. There's no next smallest number, which is why this leads it to be uncountable. For example, if you started from pure 0 and you wanted to list up all the numbers, you just can't. You just cannot, because then you'd always have to add a 1 that's beyond that one, which is why that's impossible. You cannot have that, as you see to my order. And I did talk about uncountable infinity before, in my couple of videos ago. I did talk about that. But this is like a recap to describe why it's uncountable. It cannot be placed in an order. Another way to describe it is, for example, on a... There's this famous way that can do it. There is this famous way, and I'm just... Here's an example. Look at this sheet. I have to get another one, though, by the way, yeah. Look at this. Here you see a string of A's, of B's, and C's. And just to say, I'm really sorry that for my handwriting. Sometimes I do have trouble for writing the B's, but here's what you see. For example, what you see here is that a string of A's, B's. And yes, look here. There is a maze at the back. I did print this for myself a couple of times ago. But I had no choice. I had to find one. I had to find the paper for the maze, though, but yeah. I do have a few mazes here that I just printed for myself entirely, just to do them, and I saw one, which is very good actually. So yeah, here's what it is. For example, what you see. Okay, maybe what you see here is a string of B's and C's going straight forever. They can be placed in any order. You can have C. You can have first C, then a B with infinite C's, or you can have a B and one C with infinite B's, or you can have a B and one C, and 10,000 later there's a C or B's together somehow. That you can have any order you want. There's no exact order because it's endless. First of all, to prove it to you that you can actually generate one that is not on the list, here's how you do it. First of all, look at this first one. So then at this first one, give an example of what we have to do now. That this first one, okay, I've never done this before, but here's what it is. So look at this first letter. This first letter, guys, over here is a B. So what you want to do is then flip it from a B to a C. So how am I going to do this? So C. This is the extra space on top that we're going to draw over. This is this is the first one. This is a C. Then look at this one on the bottom there is the diagonal. So this one there is a B, which is why it's on the top. So you want to change that to a C. Then look on the second one where there's a B. So that will also be a C. That one over there is also a B. That would also be a C. And that one there is also a B. So that would also be a C. So that's the way we generated it. That is like that. So basically on the diagonal, there would always be one that will generate it differently. In other words, on the diagonal, I'm going to draw it in a better, for example, the best correspondence I can do, for example, is that you start from the first and work your way down. And all I've noticed is that there's all B's, for example, the first column 1, there's a B, the second column 2, there's a B, third column 3, there's a B, and the fourth column 4, there's a B, which is why there are all C's there. But you see what I mean? If I had the fifth row, and on the fifth row there was a C in the fifth column, yeah, that would be a B on top. So fifth column, as an example to describe it for the what I mean, for example, is I'm going to draw. So there's fifth column C's, so up the add B, C, 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 the fifth column, and then you add the B there. So you're just going on diagonal, and the way you're doing this is that working your diagonal has to be different from the diagonal, okay? So this is actually a very interesting discovery that for uncountable infinity, and there's actually some people do actually use this method. I do believe a lot of videos, you will find a lot of videos talking about this exact method. I just wanted to describe this method for you guys. That on this method, because this is an interesting method discovered. So anyways guys, I just do hope that you enjoyed this video. I'll see you later guys. Bye.